Topic 7.3, probability of independent events. Two events are independent events when one event does not affect the other. An example would be flipping a coin and then flipping it again. Each coin flip is an independent event. The probability of getting tails when you flip a coin once would be 1 out of 2, or 50%. The probability of getting tails twice in a row, because those two events are independent, would be 1/2 times 1/2, which would equal 1/4, or 25%. So there would be a 25% chance that you would get tails twice in a row, theoretically. When calculating the probability of two independent events occurring, multiply the probability of each independent event together. Let's try a couple of examples. Number 1, use a tree diagram. List the possible outcomes of spinning the pointer on this spinner and tossing the two colored counter. What is the probability of each event? Landing on F, tossing red, or landing on F and tossing red? Well, when making a tree diagram, what you want to do is list the events that are happening. So event number 1 will be spinning the spinner, and event number 2 will be tossing this counter. So in event number 1, there are 6 possible outcomes. The spinner, is either going to land on A, B, C, D, E, or F. Those are the 6 possible outcomes. And for each one of these possible outcomes, there are 2 possible second outcomes. So for example, if you spun this spinner and you got A, and then you've tossed the coin, you're either going to get yellow or red. So Y for the letter yellow, for the color yellow, and R for the color red. Same goes for B, so it's going to be yellow or red. Same goes for the rest of them. Yellow or red, yellow or red, yellow or red, yellow or red. Now, what we can do is we can determine the probability of each event. So the probability of the spinner landing on F is 1 out of 6 possible outcomes. So 1 out of 6. One time out of every 6 times, it should land on F. How about tossing red? Well, tossing red on its own, it's either going to be yellow or red. Well, if we toss red, that is 1 out of 2. So 1 out of 2. Now, landing on F and tossing red, so landing on F and tossing red, in this order, would be 1 out of all of these outcomes over here. If you count them up, there are 12 of them. So the probability of landing on F and then tossing red is 1 out of 12 possible outcomes, okay? Spinning A and landing on yellow, for example, would be 1 of the 12, and so on, everything in between here. How about question 2? Each of Kelsey and Sydney has a standard deck of 52 playing cards. Each student turns over a card, then the students compare suits. Make a table to list the possible outcomes. What is the probability of each event? Kelsey turns over a spade, Sydney turns over a heart, Kelsey turns over a spade, and Sydney turns over a heart. Now, if you're not familiar with the deck of cards, there are 4 suits. There are 2 red suits. One of them is a heart, the other is a diamond, and then there are 2 black suits. One of those is a club, and the other is a spade. So there are 4 suits and 52 playing cards, and there are equal amounts of each suit. So 52 divided into 4 even groups is 13. So there are 13 cards for each of these suits. Now, what are the chances that Kelsey turns over a spade? Well, the chances would be 1 out of 4. Okay? Because there are 4 suits and there are 13 cards per suit in the deck of cards. 13 out of 52 can be simplified to 1 over 4. Now, if you're familiar with cards, you probably knew this already. You know there are 4 suits, and every 4th one should be a spade, theoretically, if they were well shuffled. Sydney turns over a heart. Well, it would be the same probability here. 13 of those cards are hearts, and there are 52 in the deck. So 1 out of every 4 of those cards should be a heart. Now, we could use a tree diagram to solve this problem, or we could take the probability of each one of these events happening on their own and multiply them together. So let's do that. Let's take the probability of Kelsey turning over a spade, which we said was 1 out of every 4, or 1/4, and the probability of Sydney turning over a heart, which we also said was 1/4. And we're going to multiply those 2 probabilities together. Okay, when you multiply fractions, remember, you just multiply straight across. So 1 times 1 is 1, and 4 times 4 is 16. So the probability of Kelsey turning over a spade and then Sydney turning over a heart, in that order, is 1 out of every 16 tries.
You can also create a table that shows all of the possible outcomes. This table, for example, shows all of the possible cards that Kelsey could possibly turn over. H standing for heart, D for diamond, C for club, and S for spade, and likewise for Sydney to the left. The highlighted cell, HS, indicates that Sydney is drawing a heart and Kelsey is drawing a spade. And you can see that there are 16 possible outcomes, and that is one of the 16 possible outcomes. So the chances of those 2 people selecting those 2 suits would be 1 out of 16.
Now, it's important to understand the difference between theoretical probability and experimental probability. Theoretical probability being that in theory, and experimental probability being what actually happens in experiments. So take this spinner, for example, to demonstrate the difference. There are 5 possible outcomes: yellow, purple, orange, red, and green. So in theory, or theoretically, if we spun this spinner, the chances of it landing on any one of those colors, let's say orange, would be 1 out of 5. Okay? Now, this virtual manipulative is going to allow us to spin the spinner 500 times, and it's programmed so that each spin is truly random, and it's going to chart our results over here. So if we spun the spinner 500 times, theoretically, how many times would each of these colors appear on the chart? Well, if our experimental probability were equal to our theoretical probability, each one of these colors should be landed on 100 times. There are 5 colors, 500 spins, each one of them should have 500. Now let's see what actually happens. So out of 500 spins, blue has got 90, it landed on blue 90 times, yellow 101, green 96, red 110, and orange 103. So this would be the experimental probability, the results of the actual experiment. Now, the more you do this, the closer we'll actually get to theoretical probability. These, if you look at the bars, they're actually not that far away from one another.